So this is an introduction to using some of the built-in solvers in SciPy. We'll solve linear equations and then nonlinear equations with one equation and one unknown, and then linear equations with several equations and several unknowns. Do a couple of examples. To solve a linear system, ax equals b, we do the following. First, we define matrix A and array B, and then use np.linalg.solve a comma b. So import numpy as np, and then define the A matrix as a two-dimensional matrix, the B array, and then np.linalg.solve a comma b, and when we print this out we get x. Pretty straightforward to solve these kinds of systems. There's a link here in the description with many more linear algebra operations, and you can see some of those here. You can take dot product, inner product, outer product. You can do matrix multiplication. There's SVD decomposition, QR decomposition, find eigenvalues, the norm, condition numbers, determinants, find trace, many other different NumPy linear algebra properties that are available. Okay, solving nonlinear equations. We've done this before using Newton's method, and Python has a built-in solver for this. It's called fsolve, which is the same name that MATLAB uses. So as usual, when solving a nonlinear equation, we first put it in the form f of x equals 0, where we know the function f and we want to find the value of x that gives f of x equals 0. To do this, we first define the function that we're trying to solve. Then we need an initial guess. Then we call the solver, fsolve. Now fsolve is part of the scipy.optimize library, so we do from scipy.optimize import fsolve, and that will give us access to the fsolve function. So here's an example. Solve f of x equals x squared minus 5 equals 0. So the first thing we do is go from scipy.optimize, import fsolve. Then we define the function, def f of x, return x squared minus 5. Then we give it an initial guess, and then we call the solver. X equals fsolve, pass it the function, pass it the initial guess, and the result gets stored in x, and then we can print out the results. And that's sure enough what we get. X is 2.236, and we can also evaluate the function with our solution. F of x is indeed very nearly 0. So we know that we've solved the function correctly. So the steps are, you need the library, define your function, give an initial guess, and then call fsolve. And this is the same kind of pattern that we had in when we were using Excel, where you would have a cell with your value for x, a cell with your function, and then goal seek, make the function 0 by varying f. So this would be like our function, this is our function, this would be our guess, and then fsolve says vary x so that f is 0 and it returns the result. fsolve. We can find another root by changing our initial guess. So here our guess was 1. If we give it minus 1, then we find the other root of this function, minus 2.23. 6067898, and the function is again practically 0, numerically 0. So pretty straightforward with a single equation in a single unknown. Again, define the function, get an initial guess, and then call the solver, fsolve, give it your function name and your initial guess, and it returns the solution. Notice that it returns the solution as an array, and we'll see why that's useful in the next section. Now, when we solve multi-dimensional equations, that is, more than one equation and more than one unknown, instead of having f of x equals 0, we're going to write this as a vector of functions which depend on a vector of unknowns, and those are equal to a vector of zeros. So notice that this has the same form, f of x equals 0, but now we've got several functions. Each one of the functions depends on the whole vector of unknowns and equals 0. So when we define our function, we're going to define a function that takes a vector and returns a vector. So You pass in a vector of unknowns and you return a vector of functions, or in other words, an array of functions. So here's an example. Suppose we have some function h of yz equals 0 and g of yz equals 0, and we want to solve both of these for the unknowns y and z. We might have the following two equations. H of yz equals y plus 2z, and g of yz equals sine of y over z. For computer solvers, we want to use a generic standard notation. We want all of our solvers to look like f of x equals 0. So we can do that by saying, let's let h be our first function and g be our second function. So we have, in an array notation, this would be f0 and f1. So h is f0, the first element, and g is f1, the second element. And each of these functions can depend on all of the unknowns. They don't have to, but we presume that they do. So we say h is a function of y and z. Those are our two unknowns. So we say f0 is a function of our unknowns, which are x0 and x1. And then for the second function, f1 is also a function of our unknowns, x0 and x1. And then on the right, we simply fill in what that functional dependence is. So in this case, the first function is x0 plus 2x1. The second function is sine of x0 over x1, which is similar to what we have. So in vector notation, this looks like array of functions, which each depend on the array of unknowns, is equal to the array of functions is equal to the array of zeros. Or f vector depends on x vector equals, that's your vector of functions, equals the vector zeros. Or f of x equals 0. So it has the same form in multi-dimensions as it does in one dimension. We just reinterpret our unknown to be a vector of unknowns and the function to be a vector of functions. So when we define our function, we'll pass in a vector of unknowns and we'll return a vector of functions. And then the solver will adjust this vector of unknowns until the vector of functions is all 0. So here's the solution for our example given above. I'm going to define f of x is our function. Y is what I'm going to return. And so I'll initialize it. I'm passing in a vector of x. I need a vector of function values, and I'll call that y. So y equals np.zeros, and then we give it the first element is x0 plus 2x1. And then we give it the second element, y1 equals np.sine of x0 divided by x1. So just like here. So y0 is x0 plus 2x1. y1 is sine x0 divided by x1. Exactly what we have right here. And then we simply return y. So we passed in a vector x. You can see it's a vector for how we use it, and we return a vector y. Then, just like before, so we've defined our function, now we need to initialize the function. So we give it an array of initial guesses. x0 equals np.array. Here our initial guesses are 1 for x0 and 1 for x1. And then we call fsolve again. X equals fsolve f comma x0. X is the function we're zeroing. x0 is our guess. The result will be a vector of solution, a vector of solutions x. And we can print that out, and we get 3.14 and 1.57. And when we evaluate the function, we can see that, in fact, both functions are practically 0. So we know that we've solved the problem. There's a link for lots more information, scipy.optimize.fsolve, and it gives you lots of other information about how to use it and other parameters that can be set, including, for instance, the tolerance and other kinds of useful information. Okay, so let's run another example. Here we have the following system of 3 equations and 3 unknowns. x squared plus y squared is 1, xy plus yz is minus 1.1, y squared plus z squared is 2, and we have a reasonable guess is x equals y equals z equals 2. And we want to do this with both Excel and Python, and here I'll just do it with Python. So let's give ourselves some space. We already have the library, but let's type it in anyway. From scipy.optimize import fsolve. Now the first thing we do is we need a function, so we'll go def f of x, and x is our variable. So to keep us from being confused about the notation, let's call this I don't know, call it capital X. And then we'll go x equals x0, capital X, y, z, 1, 2. So we could write everything just in terms of this array, but just to make it easier to write the function, I'm just going to define some convenience variables, x, y, and z. And then we need our solution, so we'll call this maybe capital F equals np.zeros. We have 3 of them. And then we can do f0 equals the first function, x squared plus y squared minus 1. And then the second function is x times y plus y times z equals minus 1.1. And then the third function, y times y, y squared plus z squared minus 2. And that shouldn't be minus equals, that should be plus 1.1. So we want it to be f equals 0, so we're going to bring this 1 to the left, and this 1.1 to the left, and this 2 to the left. So we get minus 1, plus 1.1, and minus 2. And then we can just return f. So we passed in the array, we return the array. Anything inside we can do whatever we want. So I can reassign to variables that make it easier for me to understand what's happening, so that I can define my function like it looks in the problem statement, and then I can assign that to my function f. If I wanted to, I could even do this like, I could call this like f1, f0, f1, f2, and then I could do f equals np.array, f0, f1, f2, and that would work fine too. So now we have our function. Let's give it some guess. X guess equals np.array, and we'll call that 2, 2, 2. And then finally we can call our solver. So x solution equals fsolve, give it the function, give it the guess, x guess. And we can print xsolve, and there's our solution. And in this case, let's go ahead and call the function as well, f of xsolve. See how close it is to 0, and we didn't do a very good job because our function is not in fact close to 0. So that suggests that we probably made a mistake somewhere, and in fact we did. You can see I didn't put the 2 in there. I just have y star star minus 1. That's not what I want. I want y squared minus 1. Now if we solve it, much better. There's our solution, x, y, z, and here's our functions, 0, 0, 0, numerically 0. So there we go. There's an example, 3 equations and 3 unknowns. So we write a function, pass in a vector of unknowns, return a vector of functions, and then give us a guess and solve it. Okay, let's do one more example. In this case, we want to solve the Colebrook equation for each Reynolds number listed for the given single value of epsilon over d. So let's list a few Reynolds numbers. R equals np.lin space, well, let's back up a little bit. We're going to have an array of Reynolds numbers, but we only want a single value of epsilon over d. And our function should be able to take Reynolds number and epsilon over d as parameters in addition to the unknown parameter f. And then we want to plot the solution for lots of values of the Reynolds number. So there's the Colebrook equation. F is what we want, depending on the Reynolds number and epsilon over d, and we have to figure out how to come up to a solution on this. Remember, when we're solving problems, this one's going to have several parts. We're probably going to have a for loop because we need to solve it lots of times. We're going to need an array because we'll need to solve these things, store the Reynolds number in an array and store f in an array. We're going to need to plot those arrays, and we're going to have to call the solver function inside of a loop. So that's a whole bunch of parts, and it's easy to get confused. So let's start simple and then add more functionality. Every time we do something, we'll want to verify our results to make sure they work. And ask ourselves when we're trying to start out some questions like, what are the different parts required? Well, I know that I need a function. I know that I need some arrays. I know that I need a for loop. I know that I need fsolve. So what are some useful basic things to start with? Should I start with the loop, or the plot, or the arrays, or the function, or the solver? Those are questions that you can ask yourself when trying to build up an approach to solving the problem. So let's go ahead and try this out. Well, I know I'm going to need the solver, so from scipy, and it's already listed above, but we'll practice typing it in. Optimize, import fsolve. And then I'm just going to solve it once. If I can solve it once, then I'll have a little bit of confidence that I can put it in a loop. So let's try that so that it looks like the problems we've just done. So def, my function, capital F, of my unknown, which is friction factor f, but it also wants other parameters because we were told to make it a function of Reynolds number and epsilon over d. So we'll do re eps d. Okay. And then return 1 over np.sqrt of f plus, so I'm putting all this stuff on the right on the left side so that my total function equals 0. So plus 2.0 times np.log10 of eps d over 3.7 plus 2.51 over the Reynolds number over np.square root of f. So there's my function. Now I need an initial guess. So a good guess is f equals 0.001. Maybe 0.01. That's pretty good. Now let's give it a Reynolds number equals, I don't know, 10,000. And eps d equals 0.001. Okay. Now let's go ahead and solve this. So let's change the order of these. So we have a guess, and then our parameters, and now we need fsolve. So f equals fsolve, f, comma, whoops, our function name, which is capital F, and then our guess, which is f. Now notice that you can use the same variable for your guess and your solution. So when I pass it in, that's my guess, and it's going to return f, and it'll overwrite this. But if you don't want to do that, just put fg like that. That's fine. But sometimes it's nice to not have to have as many variables floating around, so we'll just do f there. Okay, so there's our solve. Now let's see if it works. It does not work. It gives us a lot of errors, and the problem is it's missing two arguments, Reynolds number and eps d. So we can see that we want our function to have f and the Reynolds number and eps d, but our solver doesn't know how to do that. So the way that you get extra arguments in here is with the args command. Now notice above we only ever had f of x. It was one parameter and it didn't depend on anything else. But what if this also depended on the Reynolds number and we wanted to pass that in? We need to be able to tell the solver how to do that. So we do that by defining a separate argument called args equals, and then the extra arguments. So in this case, re, eps d, just like that, so that it knows the extra arguments to pass to our function. Because the solver is calling our function, and it needs to know how to call it. it already assumes that the variable that we're solving for, f, is the first one. So that's good. But it doesn't know about these other ones. And when we called it initially, it complained because it was trying to call it without giving values for RE and EPSD. So we're going to tell it about those other arguments with this args equals, and then in this case this is a tuple because it's between parentheses of these arguments. So we do args equals parentheses RE, EPSD, and that's it. And then we get our solution. So basically the same thing as before, but we have extra arguments in our function, so we give the solver the extra arguments right there. And let's see if it worked. So if we do f of f, comma RE, comma EPSD, we should get 0. Sure enough, it's practically 0. We feel pretty confident that we can solve it once. So good. Now we need to solve it lots of times in a loop. So now, instead of RE being one number, let's make it an array, np.log space from 1e to the 3 to 1e to the 8th with 100 points. And now f, let's do fg for guess. Now our solution, f equals np dot zeros. How big should it be? The same size as RE. So np.size RE. So now we have an array for our solution, and now we can put it in a loop for I in range np.size RE. So we want to loop through all the points, and if we're sick of writing size everywhere, we can do endpoints equals 100, and then we can change this to endpoints, and this to endpoints, and this to endpoints, like that. And then we can go f of I equals fsolve, the function, our guess, f guess, and then we need args equals our Reynolds number, which is REI, comma EPSD. And that seemed to work. Just so we can see the output, let's print it, print fi, and maybe our function, make sure it's 0, f of fi, comma REI, comma EPSD. And sure enough, they're almost always 0, and the friction factor tends to be about 0.02-ish, so maybe we can give it a better guess from now on. There we go. Okay, now that we've got our function, we can plot it up. Let's add our plotter to the mix here. Import matplotlib.pyplot as plt, %matplotlib inline. And at the bottom we can go plt.plot, and we want RE on a log scale, so we'll do np.log10 of RE and plot the friction factor, and then let's add a label, x label, and we've got log 10 of RE, and y label is friction factor. Plot it up, and there we go. Oops, $, like so. Much better. And if we want to change these font size 16, just a little bigger, and there's our plot. Okay, so we started with just the function, no arrays, no nothing, see if we can solve it once, and then we turned RE into an array and F into an array, and we called our solver inside of a loop. Again, each time we call it, we're just calling it with a value, but now it's a different value of the array, and we're storing the result in a new value, so we can solve it each time. And you can also think about how you would do this problem in Excel as review for solving equations in Excel. There you go.